Alrighty, hi everyone. Welcome to the third ANSYS tutorial. Today we're going to be doing more pipe flow, kind of like what we did on the first lesson, but we're going to explore a little bit more on the different types of flows that you can see through a pipe. So first we're going to go to geometry as we always do, right-clicking and going to design modeler. Now we're just going to wait for that to pop up. Okay, let's switch over. Alrighty. Now I'm going to start going a little bit faster on this section because this has been explained in previous tutorials. So I'm just going to go to a rectangle, make it. I'm going to set its dimensions. Same as before in the first tutorial. Ooh, one thing I do want to note, for this particular case, I want to take the units and switch them to millimeters on the top left here. Hitting units, you can set them to whatever you want. I'm going to use millimeters. And it's important that we do this just so that we can make sure that the second flow that we're going to explore happens properly, because it can be a little picky. So for the vertical distance here, we're going to use a 10 millimeter distance. And then on the horizontal, we're going to use 500 millimeters. So I'm going to have to zoom way in to catch the pipe. There we go. So now I'm just going to turn this into a surface, same as before. Surfaces to sketches. Hit your object and generate. There we go. That's all we need to do in here. So now I'm going to go to the meshing section. Just double clicking on the mesh part under the workbench. I'm going to stop the share while we wait for that to pop up. There we go. Okay. Meshing. Alrighty. So now we're back to the meshing section. Going to go to the mesh. Now I'm going to select sizing, hit the line here, apply the geometry, go here to number of divisions, and I'm going to put 400 divisions here. And always remember, put the behavior to hard. I typically forget this and it makes your mesh weird. So you have to make sure that you make it hard. Same thing for the vertical parts, down to number of divisions. I'm going to set 150 and make it hard. Then I'm going to apply face meshing, select the whole surface. I'm going to generate the mesh. And if I'm going a little too fast to the first tutorial, I do basically this process a lot slower. So if you need to see this again, just go to the first tutorial and it should help you out. Alrighty, so now I'm going to go ahead and create my named sections. I'm going to call it the inlet. In this situation, well, first I'm going to define my outlet. Then I'll explain that right now we're going to want to name each wall something different. So I'm going to do top wall and bottom wall. And I'll show you why this is necessary later. So now I'm going to go back to the workbench. I'm going to update the mesh. Then I'm going to go to setup. And now under the setup here, same as before, you do double precision. You always do double precision when you start it. Now Fluent's going to appear. All right, I think it's ready. We're going to go to models. For this one, I'm going to go ahead and use a laminar model right here. That's all you need here. Under materials, we're going to go to air. We're going to change its properties again to what we need. So I'm going to make the density 1. And then under the viscosity, make it 1e to the negative 4. Change and create. Now we're going to go to the boundary conditions, go to the inlet, set its velocity to 10 meters per second. That's all we need there. Go to reference values and compute from the inlet so that it catches all the values that we just entered. Initialize as always. And now we're going to run. Oh, I forgot to change the iterations to 500. There we go. Now we can run the calculations. And this shouldn't take that long. It's a fairly simple flow to calculate. There you go. Alrighty. Now we're gonna go to the results section. CFD post. Alrighty. So now I'm gonna make a contour. You press this little button up here. Change the location to symmetry 1. Then change this to velocity. And apply 50 contours. Now, this is pretty much what we saw in the first tutorial. What this is called is a Coil Flow. And essentially what's happening, let's zoom into the beginning here. So in here, this is where the flow starts. And I explained in the first tutorial how there's boundary layers. In that you can see one boundary layer on the bottom here, the other one coming up here. And that as you go along, these boundary layers grow. And it acts as a funnel, a nozzle is the proper term. It's a nozzle here, so that as this diameter that the central flow goes through narrows, it increases in velocity. So you see that over here, when the flow is called fully developed, this is essentially the maximum velocity of what? 1.4 e to the 1 meters per second. So that's 14 meters per second over here. So I'll help illustrate this by actually putting on a graph to show you what the velocity is at different locations. So this part I'll go slower since you haven't seen this before. So if you look on the top left, there's the insert button. And this is how you can also put in a contour, streamlines, or vectors. But you see this location button, hover over it, and you'll see line. So I'm going to do this as 1/4. Oh. 1/4. You cannot use numbers in the name, so I'm just going to name it that. So essentially, the way that this works is you define 2 points on 3D space for your line to be at. And then what you can do with it is you can actually calculate the fluid properties along that line. So the dimensions that we have are 500 millimeters by 10 millimeters. And this part here is strictly in meters. So you have to convert all of these numbers into meters. So we have 0.5 meter for the length, and then 0.01 meters for the height. So if we look here, we have 0.1 and 0.2, and these three numbers. We have x, y, and z coordinates. So the way that it works is that first you go to 0.1 and you decide, okay, where do I want 0.1? Well, this first line, I want it to be 1/4 of the way along the pipe. So I want it to be 1/4 of 0.5 meter. So I am going to stick that on 0.125, I believe. Let me make sure that I am correct. Yeah, 0.125. So this is on the x-axis, it's going to be 0.125, somewhere maybe around here, meters into the pipe. And 0 in the y, meaning that's just going to stick right on the bottom of the pipe here. For 0.2, I'm going to change this over to, so we want this to be on the same x-axis because we want the line to essentially sit vertically along the pipe to get the 1/4 mark along the y-axis. So I'm going to leave the x as the same, but for this one, I want the point to be on the top of the pipe. And as we determined earlier, that y-coordinate was 0.01. And one last thing, number of samples is essentially how many samples along that line ANSYS is going to take to calculate, whatever you want to get. So I'm going to make this 100 samples. That should be enough to get a fairly smooth graph. Now I'm going to apply it. And I'll turn off the contour to help you see. Here is the line. So you can see that is 1/4 of the way. The first point sits right on the bottom. Actually, I'll zoom in a little bit to help demonstrate this further. So you can see how 0.1 is this bottom point, 0.125 meters to the right, but 0 meters in the y. That's why it's sitting right on the bottom. And then for 0.2, it's on the same place on the x-plane, but we just made 0.2 sit on the top of the pipe. So the whole line is sitting here, which is exactly what we're after. So now we're going to insert 2 more lines. I'm going to do one more. I'm going to do this middle. So same process, x-axis, we want to do the bottom point first. So it's 0.5 divided by 2, which is 0.25. This stays at 0 so that it sits on the bottom. Then I'm going to do the same thing for the x-axis, but change the y value to 0.01 and put 100 samples. Then we can see that a second line appears at the middle of the pipe. And I'll put one last one. I'll put it at the end, actually. Insert location line. And of course, you can put these lines wherever you'd like. If you wanted to put one, closer to the back here where the flow was originally starting, let's say you wanted to put it here so they can see what's going on in the very early stages of the flow's development. You can put a line here, knowing what the x distance is here, or you can put one, somewhere over here where it's fully developed. I just made arbitrary choices. Oh, the other way that you could make the lines is you could just hit the location button right here and just automatically go to lines. So you can either go to insert like I did before, or just hit location up here. So I'll put end. So now for the x-axis, I want it to be all the way at the end here. So that's just the length of the pipe at 0.5 meters. 0 and y, because that's how I've defined it so far. Same x, and then we want it on the top of the pipe. And of course, 100 samples. Perfect. Now you can see that there's a line there. So what does this do for us? Well, if I go up to insert, and you go all the way down to chart, I'm going to put in a new chart. I'll call it velocity. Nope. Chart. That's better. Okay. So now we see this blank chart. So now we're going to populate this with the data that we're going to collect. So I'm going to make this velocity of fluid along pipe. You don't have to change anything else here. Go to data series. Now, each series is essentially a line that you will see on the graph. So I'll name the first series, or the first line, let's say 1/4. Now we're going to go to location. This is the data source, where ANSYS is going to get the data from. So if we go to location, we can see the lines that we applied earlier. So I can hit 1/4. Now I want to put all of these on the same chart. And the way that you do that is you go to this little button here, hit new, and you make a second series that will also populate this chart. So I'm going to call this half, or middle, just to be consistent. Then I'll go to the middle, create one more new one, call it end, and go to the end. Now we have 3 different series, so 3 different lines will appear here once we've established our x and y axes. So let's do that now. Under the x-axis, you can see a bunch of stuff. You hit variable here. There's going to be a drop down. We'll make this velocity. But of course, you can make it any parameter that you need, depending on what you're looking for. On the y-axis, we're going to just go all the way down and hit y. So what we did is our x-axis is going to be the velocity of the fluid, and the y-axis is going to be the y direction up along the pipe. So now we don't have to do anything else. We hit apply, and there you go. So now there's 3 different lines that show the velocity on the 3 different locations that we defined in the pipe. So the red one is 1/4 of the way through. The middle one is, of course, at the middle, and the end is green for the one at the end. So now let's analyze this for a second. If you imagine the y-axis is that y direction on the pipe. So if we go back to the 3D viewer, the y-axis is the vertical part of the pipe here, the cross section of the pipe. And this velocity, if we look, you can see how the contour shows that, say on the bottom here, it's at 0 meters per second due to the no-slip condition that I described in the first tutorial. And as you go up, we have the boundary layer here where the fluid is going a little slow, which if we look back at the chart, a little bit lower, there's very low velocity at the bottom and at the top of the pipe, which you can see by the blue and green colors down here on the pipe. But when you go to the center, after the boundary layers begin to act like a nozzle, you see that at the middle, the velocity picks up, which if you look here at 0.05, or yeah, 0.005, sorry. The velocity is at its maximum because that's at the center of the pipe where the, of course, velocity is at max. The other thing that we notice is that on the 1/4 way, the maximum velocity is here, 13 point something. But as we go along the pipe, the velocity tends to increase. If we look back at the 3D viewer, you can see that as we go along the pipe, the boundary layer increases in size, but this middle region becomes more red, which means that the velocity of the fluid is increasing. And so that's what it means for a fluid in a Coil flow to become fully developed. That's when it becomes at its maximum here. And if we go back to the 3D viewer, you can see that over here, nothing's changing. The boundary layers are at the size that they like, and the velocity of the fluid at the center is at its maximum. So over here, it's fully developed. But if we go back, this area where the velocity is picking up and the boundary layers are increasing in size, this is where the fluid is developing. And so you can kind of see that in the chart, that the fluid is still developing here, and by the end, it is fully developed. So that's what you can understand by putting everything on a chart. So now what I'm going to do is I'm going to change the parameters of this flow to produce what's called a Coil flow. And essentially what it is instead of having a velocity at the intake here, the velocity is 0 here, but the top part of the pipe here is moving. Like if you imagine 2 plates on top of each other with a fluid in between them, the top one moves, the bottom one does not move, that will produce a Coil flow. And that can happen, let's say you have a machine part that you have lubricant, and you have 2 parts, 2 plates slapped on each other, and you lubricate the middle. The fluid flow of your lubricant will be a Coil flow because the top part of whatever machine we're talking about is moving, but the bottom is not. And I'll illustrate what that actually looks like to you right now. So the way that you would do it, you don't have to redo anything. It's one of the beautiful things of ANSYS. I'll show you how to change the parameters of the flow just with the same exact simulation that we created. So let me share my screen back to Fluent. So now we go back here. And the way that it works is that if you change something here, the post part of ANSYS will detect that there has been new data coming in, and it'll actually change your simulation based on the new parameters that you put in. So here's the changes that we're going to make. We're still going to use a laminar flow. We're going to go to the air and we're going to increase the viscosity. This just helps the Coil flow behave a little bit more. It's a lot easier to get the proper relationship that we want by doing that. Now we're going to change our boundary conditions. We're going to go to the inlet. As I said before, this should be 0. But another thing that we have to do is you have to actually turn this into a pressure inlet. And this just really tells ANSYS like there is absolutely nothing going on. When I just really quickly, this should be at 0. The gauge pressure should be at 0. That just means that there is no pressure difference between the inlet and the outlet since they both have a gauge pressure of 0. So now the other thing that we're going to go and do, top wall, as we defined earlier, and this is why we needed to separate the top wall and the bottom wall. That way we do not touch the bottom wall so that it's stationary, but we put the top wall, hit edit, and then we're going to go to a moving wall here. Put the speed, I'll put it to 1 meter per second, and everything else can stay the same. I'll just do a really quick rundown of what's going on. You don't have to change this. Rotational just means that that part will rotate, and in future ANSYS tutorials, we will actually use rotational. And components I've never used. I'm sure that it means that it both translates and rotates. In direction here, this just defines essentially the direction vector that the velocity is going. So you see that we have 1 in x, 0 in y. So that means that the plate will move in the positive x direction. And this number, it should be a unit vector because it's just pointing in a direction. So if I did, say 0 for x and 1 for y, the plate would move upwards. But that's not what we're after. We want the plates to slide along each other. So we will not touch the direction for now. So with that, we'll hit OK. Nothing else needs to change to my knowledge. So we're going to go back to reference values. We're going to go back to Inlet to make sure that the Fluent knows that we've changed stuff. Initialize. Now you see this little error. Don't worry about this. The simulation will run just fine. Then we're going to calculate again. Yeah, this one can take a little bit longer. And I know that the residuals here went up, but they usually make a rebound and go down. There we go. There we go. So now I'm going to change my screen back to the post. And now we can see this new little window here. New upstream data found. A new upstream data exists. Would you like to refresh the simulation? Hit yes. And now ANSYS will automatically change your simulation to match your new parameters. As you can see, still the same pipe, but the flow is very, very different because it took account of the new data. So what's going on here? Well, we can see something strange happening. We have this at 0 due to the no slip condition, but the velocity of the fluid up here is almost 10 or almost 1 meter per second. And that as we go up the pipe, the fluid's velocity increases. And actually, this is increasing linearly, which is the big defining factor of a Coil flow. And the reason why the fluid up here is pretty much going at 1 meter per second is because of the no slip condition. Any fluid that's touching the surface is going to go at the velocity of that surface. So this top part of the pipe is moving, or this top plate now is moving. This bottom one is not moving. So any fluid touching the bottom plate is at 0. Any fluid at the top is at 1, or should be at 1. So now we're going to go to the chart. Oh, this is not updated. Let's apply again. There we go. So now you can see something interesting happening. At the 1/4, middle, and end, all of it is the same, and it is linear. So as you go up along the pipe, the velocity of the fluid is increasing linearly, which is exactly what we're after for a Coil flow. And you can see that pretty much at the entire length of the pipe, except for in here, but that's just because it's way at the beginning. But for pretty much the entirety of the pipe, it has that linear relationship. So that should make sense of the Coil flow. Now what I'm going to do is actually do a combined flow. So this is any situation where you have two plates and the top one is moving, or the bottom one. But really when one plate is moving and you have a velocity at the inlet. I can't think of an example so easily off the top of my head of this happening, but it's still good to know how to do this. So we're going to do the same thing as we did before. I'm going to go back to Fluent. And I'm going to change the parameter. I'm going to go leave air as it is. It's completely fine. We're going to go back to boundary conditions to inlet. Change it back into a velocity inlet. And now we're just going to put 1 meter per second as the inlet velocity. And that's actually the only change that you need to do. Just go back to reference values and use inlet so that it can catch the new velocity. Initialize. Then you run your calculations. Yet again. And this method of going back to the calculations and redoing them works for any kind of simulation. You can do this as many times as you want. And that's one of the most convenient parts about ANSYS. It's that you can always go back and just do it again, and then you can just refresh your simulation. And then it'll take a second to load, and then everything will change, which is exactly what we want. So now this is a completely weird flow, not quite like what we've seen. So what's happening here? Well, let's analyze it. On the bottom, it's still 0, as it should be, because the bottom plate's not moving. And then as we go up, the fluid's flow is kind of increasing. But unlike a Coil flow, obviously this is not a linear relationship. The maximum velocity is at this point, not at the top. But it's not quite like a Coil flow, because there isn't that boundary layer on the top here that's creating that same nozzle effect. There's the one on the bottom, and sure, it's kind of creating a nozzle, but it's not happening at the top. So in essence, what's going on is that the velocity increases, has its maximum here, and then tapers off to match the velocity of the top plate again. And we can see that the orange region is about in the 1 meter per second region, which is the velocity of the top plate. But the red part is on 1.3, which is a little bit bigger. Let's look at the charts. Let's apply it again. There we go. So now we can see that no matter where in the pipe we are, the velocity profile here is actually the same, kind of like a Coil flow, but it increases as you go up, has a maximum 0.06 to 7 along the way, and then it decreases down to 1 meter per second, which is the velocity of the top plate. So this is essentially what a combined flow looks like. And of course, depending on, if the velocities were different of the top plate and the inlet velocity were different, this might go up or down. But the bottom line is that it combines the properties of both the Coil flow and the Coil flow to make this combined flow here. And of course, what the chart shows is essentially illustrated by the contour here, by how it increases maximum around here and then tapers off back to the velocity of the plate. So that is actually all that I wanted to show you for today. Oh, don't concern yourself with the very beginning. Like before with the Coil flow, it's just small development of the boundary layer happening here. So I suppose like a Coil flow, it does need some time for this bottom boundary layer to develop before it fully develops into this part. But you can see that there is very little distance necessary to actually fully develop the flow into the combined flow. And we didn't see this region here because we never even put lines there. Our lines are starting here. So if you wanted to go back, do the simulation and see what is going on here with the velocity, all you need to do is put a line here, as I showed you earlier before doing the Coil flow. And then you can chart it and see what it looks like on here. But yeah, that sums up the third tutorial. If there's any issues, you can message either me or Camilla for any questions. I hope you enjoyed, and I hope to see everyone in the next ANSYS tutorial.